Welcome to our lecture on security models and operating system security. My name is Dr. Dwayne Hodges, and I'll be guiding you through the foundational concepts that shape secure system architecture and design. In today's digital landscape, security is not just a feature, it's a fundamental requirement. Understanding security models and how operating systems enforce security is crucial for anyone working in IT, cybersecurity, or system design. We'll explore the core security models that define how access control and trust are mathematically structured. You'll learn about the Trusted Computing Base, TCB, the reference monitor, and how these concepts create the backbone of secure systems. We'll discuss practical OS security mechanisms, common vulnerabilities, and strategies for hardening systems. Think of this lecture as building the foundation for all your future work in secure system design. Whether you're preparing for certifications like CISSP or working on real-world projects, these principles will guide your approach to security. Let's dive in and see how security models and operating system mechanisms work together to protect information and maintain trust in computing environments. Before we dive into the details, let's clarify what you'll be able to do by the end of this lecture. These objectives will guide our journey and help you focus on the key takeaways. First, you'll be able to explain several formal security models, including Bell-LaPadula, BIBA, Clark-Wilson, Brewer-Nash, and non-interference. Each of these models addresses different aspects of security, such as confidentiality, integrity, and conflict of interest. Next, you'll understand the Trusted Computing Base, or TCB, and the reference monitor. These are foundational concepts that define how trust is established and enforced within a system. We'll discuss operating system security mechanisms, like process isolation, memory protection, and hardware-based solutions such as Trusted Platform Modules, TPMs. You'll see how these mechanisms work together to protect the system. You'll learn to identify common vulnerabilities in operating systems and discover best practices for hardening and securing them. Finally, I will provide you an optional opportunity for some hands-on activities where you'll gain an understanding of multi-level security concepts, which are essential for environments where information is classified at different levels and access must be tightly controlled. Keep these objectives in mind as we move through the lecture. By the end, you'll have a solid foundation for understanding and applying security models and mechanisms in real-world scenarios. Now let's explore the formal security models that form the backbone of secure system design. These models provide mathematical frameworks for defining and enforcing access control in computer systems. Focuses on confidentiality. Its rules, no read-up, no write-down, ensure that users cannot access information above their clearance level or leak sensitive data to lower levels. Prioritizes integrity. It uses no write-up, no read-down to prevent unauthorized modification of higher-level data and contamination from lower-level sources. Emphasizes well-formed transactions and separation of duties. It ensures that only authorized, validated processes can modify critical data, reducing the risk of fraud or error. Addresses dynamic conflict of interest situations, such as in consulting or financial environments, by restricting access based on changing business relationships. Prevents information leakage by ensuring that actions at one security level do not affect what can be observed at another level. Each model serves a specific purpose, whether it's protecting confidentiality, integrity, or preventing conflicts of interest. By understanding these models, you'll be able to select and implement the right controls for different security scenarios. With these models as our foundation, we'll next look at how trust is established and enforced within a system through concepts like the Trusted Computing Base. Now that we've covered the main security models, let's talk about how trust is actually enforced within a computer system. The concept at the heart of this is the Trusted Computing Base, or TCB. The TCB is the collection of all the hardware, software, and firmware components that are responsible for enforcing the system's security policy. If any part of the TCB is compromised, the entire system's security can be at risk. A critical part of the TCB is the reference monitor. This is a conceptual model that must be tamper-proof, always invoked, and verifiable. The reference monitor mediates all access between subjects, like users or processes, and objects, like files or devices. The security kernel is the actual implementation of the reference monitor. It's the core part of the operating system that enforces security rules. The TCB defines the system's trust boundary. Everything inside the TCB must be trusted to operate securely. Everything outside is considered untrusted. Understanding where this boundary lies is essential for secure system design and for evaluating the risk of potential vulnerabilities. Next, we'll look at how different security modes of operation use these concepts to enforce security in various environments. Now, let's discuss the different security modes of operation that determine how systems enforce access control based on user clearance and need to know. There are four main security modes. All users have the same clearance and need to know for all information processed on the system. This is the simplest mode, but not always practical for diverse environments. All users have the required clearance, but not everyone has a need to know for all data. Additional controls are needed to prevent unauthorized access within the same clearance level. Access is further restricted by dividing information into compartments. Users need both the appropriate clearance and specific compartment authorization. Users with different clearance levels and need to know can access the system simultaneously. The system must enforce strict controls to prevent unauthorized access or information leakage between levels. A common example is a multi-tenant cloud environment that enforces multi-level security, MLS, ensuring that each tenant's data is isolated and only accessible to authorized users. Choosing the right security mode is critical for balancing usability and protection, especially in environments handling sensitive or classified information. Next, we'll look at the specific mechanisms operating systems use to enforce these security requirements and protect against threats. Now let's look at the specific mechanisms that operating systems use to enforce security and protect against threats. The operating system keeps processes separate from each other, ensuring that one process cannot interfere with or access the memory of another. This is fundamental for preventing attacks where malicious code tries to access sensitive data from other processes. Modern CPUs use privilege rings to separate different levels of access. Ring 0 is the most privileged, kernel mode, while Ring 3 is the least, user mode. This separation helps contain the impact of vulnerabilities and limits what user applications can do. Hypervisors allow multiple virtual machines, VMs, to run on the same hardware, each isolated from the others. This isolation is crucial in cloud environments and for running untrusted code safely. TPMs provide a hardware root of trust. They securely store cryptographic keys and measurements, such as the endorsement key, EK, storage root key, SRK, and platform configuration registers, PCRs. This helps ensure that the system boots securely and hasn't been tampered with. Ts create secure enclaves within the processor, allowing sensitive operations to be performed in isolation from the main operating system. This is especially important for protecting cryptographic operations and confidential data. Each of these mechanisms works together to create layers of defense, making it much harder for attackers to compromise the system. Understanding how they function helps you design, configure, and maintain secure systems. Next, we'll examine common vulnerabilities in operating systems and discuss best practices for hardening them against attacks. Even with strong security models and mechanisms, operating systems remain a prime target for attackers. Let's look at some of the most common vulnerabilities and how we can harden systems against them. Attackers may try to exhaust system resources, causing legitimate processes to fail or the system to crash. This can be done by overwhelming memory or processing capacity. Exploits that allow attackers to gain higher privileges than intended, sometimes even full control over the system. Kernel vulnerabilities are especially dangerous because the kernel has the highest level of access. Systems that are not regularly updated or properly configured are at greater risk. Attackers often exploit known vulnerabilities that have not been patched. Provides mandatory access controls for Linux systems, restricting what processes can do, even if they are compromised. Allows administrators to control which applications and files users can run, reducing the risk of malware execution. Ensures that only trusted software is loaded during the boot process, protecting against rootkits and boot-level malware. Hardening is about reducing the attack surface, removing unnecessary services, applying patches, and enforcing strict policies. By combining these tools and practices, you can significantly improve the resilience of your operating systems. Next, we'll discuss how security evaluation frameworks help us measure and validate the effectiveness of these security controls. Now that we've discussed how to secure systems, let's talk about how we measure and validate that security. Security evaluation frameworks provide standardized ways to assess whether a system meets specific security requirements. The Trusted Computer System Evaluation Criteria, often called the Orange Book, is one of the foundational models for evaluating computer security. It introduced the concept of security classes and requirements for confidentiality and integrity. This is the international standard for computer security certification. Common criteria allows organizations to specify their security requirements and have products evaluated against those requirements, making it easier to compare and trust security solutions globally. Under common criteria, products are rated from EAL1, functionally tested, to EAL7, formally verified, designed, and tested. The higher the EAL, the more rigorous the evaluation process and the greater the assurance that the product is secure. These frameworks help organizations make informed decisions about which systems and products to trust. They also provide a common language for discussing security requirements and assurance levels, both within organizations and across industries. Next, we'll look at a real-world case study to see how these models and frameworks are applied to prevent security breaches. Let's bring these concepts to life with a practical scenario, a case study that highlights the importance of security models and enforcement mechanisms. Imagine an insider who has top-secret clearance and attempts to modify data at a lower classification level. This situation is a classic example of the risks posed by insiders, even those with high levels of trust and access. The Bell-LaPadula model is designed to prevent this exact type of breach. Its no write-down rule ensures that users with higher clearance cannot write or modify data at lower levels, protecting against unauthorized information flow. This model is especially important in environments where strict confidentiality must be maintained, such as government or military systems. The Trusted Computing Base, TCB, and operating system enforcement mechanisms reinforce these rules. The TCB ensures that only authorized actions are permitted, and the operating system's security kernel implements these controls, making it difficult for even privileged users to bypass security policies. By combining formal security models like Bell-LaPadula with robust system enforcement, organizations can significantly reduce the risk of insider threats and maintain the integrity of their data. Next, we'll review some key terms to reinforce your understanding of the concepts we've covered. Before we wrap up, let's review some of the essential terms you've encountered in this lecture. Understanding these will help you communicate clearly about security concepts and apply them in practice. Bell-LaPadula focuses on confidentiality using rules like no read-up, no write-down to prevent unauthorized information flow. BIBA prioritizes integrity, ensuring that data cannot be improperly modified or contaminated. Clark-Wilson enforces well-formed transactions and separation of duties to maintain data integrity. Trusted Computing Base, TCB, the set of components responsible for enforcing security policy. Reference Monitor, the conceptual model that mediates all access and must be tamper-proof, always invoked, and verifiable. Security Kernel, the implementation of the reference monitor within the operating system. TPM, Trusted Platform Module, hardware providing a root of trust for secure operations. TE, Trusted Execution Environment, isolated processor enclave for sensitive computations. Common Criteria, International Standard for Security Evaluation. EL, Evaluation Assurance Level, rating system for the rigor of security evaluations. Familiarity with these terms will help you navigate security discussions, exams, and real-world scenarios with confidence. Next, we'll look at your assignment and how you can apply what you've learned. To reinforce what you've learned, let's look at your assignment for this lecture. These tasks are designed to help you apply the concepts and models we've discussed in practical scenarios. So here is your optional assignment. I'd like for you to compare Bell-LaPadula versus BIBA models. Analyze the differences between these two foundational security models. Consider their focus, confidentiality for Bell-LaPadula and integrity for BIBA, and how their rules, no read-up, no write-down versus no write-up, no read-down, affect system design and policy enforcement. Next, explain virtualization's effect on trust boundary. Discuss how virtualization technologies, such as hypervisors and virtual machines, change the traditional trust boundary in computing environments. Think about how isolation, resource sharing, and hardware-based security features impact the way trust is established and maintained. For some additional reinforcement, I do encourage you to please read Chapter 9 of the CISSP All-in-One Guide. This chapter will deepen your understanding of security models, operating system security, and related best practices. Take your time with these tasks. They're meant to help you think critically and connect theory to real-world applications. If you have questions or need clarification, feel free to reach out or bring them to our next session. In our final slide, I'll share some closing thoughts to wrap up today's lecture. As we conclude this lecture, let's reflect on the key messages. Security models are not just theoretical, they define the logic of trust that underpins every secure system. By understanding and applying these models, you can design systems that are resilient against a wide range of threats. The integrity of the trusted computing base is fundamental. If the TCB is compromised, the entire system's security is at risk. Always consider where your trust boundaries lie and how you can minimize what needs to be trusted. Security evaluation frameworks like Common Criteria and the Orange Book provide a way to measure and validate the effectiveness of your security controls. They help ensure that your systems meet the required assurance levels for their intended use. Remember, a secure system is not an accident, it's a design. Security must be intentional, built into every layer of your architecture and processes. Thank you for your attention and engagement. I encourage you to review the material, complete the assignment, and feel free to schedule some time with me if you have additional questions. Or feel free to bring our questions to Out Next live session.